So my name is Jacob Graham, and I did the Clapeyron experiment with my group throughout the class period. So the purpose of this experiment was to measure a flask, which we depressurized. We put it in a vacuum, and we put it into boiling temperature, and we measured the data points as it went up, and we want to find f of g by using this Clapeyron equations that we learned in German class. So basically the procedure was we had a flask, we had one flask with beads, one flask was out, and like I said, we put it in vaporization conditions. We went from 2 psi back to atmospheric, which was 14.7 psi, maintaining boiling conditions throughout, and we had it measured through the computer system, and we had measurements for all the points in between. So this is pictures from the experiment. Here you see the flask without the beads. Here's the flask with the beads, and you see that the bubbles are going way faster in the flask with the beads than without the beads. And just to note, I'll talk to you later about why we use beads in one flask and why that's a better choice to make during this experiment. So here, this is just the top two charts are basically where I took the points that we measured, I put it on Excel, and here's a P versus T, pressure versus temperature chart. The left is the chart without the beads, the right is with the beads, and this is actually graphed results from the pressure tables, which for saturated liquids we got from our thermodynamics book. So calculating f of g, how I calculated f of g, basically we have this function, and basically the first way that I decided to try to calculate f of g, h of f of g is basically using the equation and using a local derivative, and with this local derivative, dp over dt, basically plug that in for that local spot, plug in the temperature for that local spot and the pressure of that spot, basically plug in. Oh, I also had some trouble because I used the wrong R. I realized that I needed to use the specific gas constant and not the 8.3134 gas constant. So I plugged all that in, and this is the result that I got for the flask with the beads, and this is for without the beads. So 2,480, 2,500, around the same spectrum. Now, I compared it to the tabulated results, and it shows that it should be 2,332.7. So there is some error, and here I just measured how much error with the beads was a little bit more accurate. It got to 6.15% error with the beads, 7.6 error without the beads. And the sources of error, why did we get error? So partly it's because we used a local derivative. There's going to be more error with a local spot taking one measurement. So another way that we could do this is basically taking the derivative, I plotted it on Excel and I found a slope fit, a curve fit, and we can plot that entire function. I'll show you on the next slide, and plug it into the formula. So here you see that I actually have the whole function here, and then you have the derivative of that function here, and basically you can plug it in to both of these equations and get a better result, and that would be a better way to try to solve this problem and get more accurate answers. Now, why did we add the beads? Basically, the experiment with the beads took only 10 minutes and 30 seconds, whereas the one without the beads took 28 minutes and 52 seconds, and that's why we use the beads. We also got some more accurate results, but also I remember Dr. Wong talking to us in fluids class. The beer bottle, when you open it, the first bubbles occur somewhere where there's some air inside a glass bottle. So the beads are creating some obstacle for the bubbles to actually form and for the process to become faster and for the pressure to go up, and it just speeds up the whole process by a third. So we experienced this phenomenon really in a real life situation. Scuba divers have to think about this situation that as they go up from the depths, and they go up to the surface. Basically, you're experiencing like a vacuum. You're going into really high pressure into lower pressure, and your body, when you're in depths like 40 meters, basically your body is experiencing conditions which are not normal. So when you get into that stabilization, like 40 meters underwater, your body creates, your bloodstream has bubbles, nitrogen bubbles, which equalize. But when you go up too fast, you have to be careful because those nitrogen bubbles expand, because similar to this, the boiling point was much lower. The flasks were boiling at like 50 degrees centigrade when in regular atmospheric conditions it boils at 100. So same thing in our bodies, we can develop nitrogen bubbles, which can cause cardiac arrest and brain aneurysms and really dangerous side effects. And that's called air embolisms, and that's something divers need to be aware of and take precautions for. And that is really my slide. Are there any questions?
6 minutes and 5 seconds.